Go ahead and record this session too. I'm gonna start actually uploading these sessions to YouTube as well. So like if there's any reason somebody misses one or anything like that, like from right now I just started the recording, so then I'll end it after the lecture part, and after I walk everybody through the lab, and I'll just end it there, and then questions get answered, and I'll just leave that stuff off the record or whatever. But I have some students that are like in different parts of the different parts of the world, and for them it's like 3 a.m. right now and stuff like that. So it's like SDSU like increased the tuition on people, and then they made everything online, and they jammed extra classes together, and like they made all the classes bigger. So it's like, there's gonna be a certain kind of relaxed nature I'm gonna put into this class just because of how ridiculous the circumstances are. So I just want everybody to know to like not freak out. If it's taking too long and you need something to go do, if it's been like 2.5 hours and you need to go do something, that's okay, right? Like maybe get your group members' contact information and stuff like that, and you can always work together later if you want, right? I just wanted to mention that. If anybody has any issues, please email me, let me know. I'll work something out for you. But this is kind of how I'm going to try to like alleviate any load issues here. Anywho, so let me just rename this really quick. So today we are doing Lab 2 Vector Addition. Now, I'll start this off by saying what the hell a vector is. And now, here's the thing. A lot of this is going to be review for a lot of people. And some people might not have had to actually like deal with this stuff for a while, might not have to think about it for a while. Some of you might have. So my apologies if it goes a little slow for some people. I'm going to try to go through stuff that I feel like you've all seen before a little quick, but I also want to mention it just so everybody has the tools. Now, that being said, I'm going to start with defining what a vector is for the next 20 minutes. No, I'm just kidding. For the next couple of seconds here. Last time we worked with something like 65 miles an hour, right? And that right there is a scalar. Okay, that's just, it doesn't have a direction. It has no direction. So it's just a value. And so just a value in physics, we call it a scalar. Today we'll be working with things like 65 miles per hour northbound. Okay, this here is a vector because it has a value plus a direction. Okay, so last time we just worked with values, changing the units of them and so on and so forth. Today we're going to work with values attributed to some direction, some vector, okay? Now, the way we're going to work with that is by working with lines, right? Lines at a certain angle with a certain amount of value to them, magnitude. Now, we're going to work with forces, okay, because those are nice. You can be like you pulling on something in a certain direction, and that's essentially what we're going to be doing. We're going to be calculating things that were essentially as if we're like pulling on them at some degree angle with respect to some 0 degree, okay? Now, what I mean though is like, let's say if I start out by saying, let's say we have a force of 50 newtons, and don't worry about newtons right now, just a unit. I'm not even going to write the units for all these things. I just really wanted to describe to you guys vector decomposition, but it's a force and it's in newtons, and the lab does talk about newtons versus mass, and so I'm going to mention that before I let you go. But okay, so the force is 50, right? And the angle, theta, which is just a Greek placeholder, is a Greek letter for a placeholder for what I'm going to have an angle in there eventually. I'm going to say it's 60 degrees. Okay, so that should be everything you need to know, right? Except, wait a minute, no, it isn't, because where the hell is 60 degrees? Is that here? Is that there? Is that down here? 60 degrees with respect to what, right? So we're going to operate off of the typical XY coordinate grid, okay? There's your positive X direction, negative X direction, positive Y direction, negative Y direction. But also, this is going to be 0 degrees on the right, 90 degrees on top, 180 over here, 270 down here, and then back to 360. Okay? So that's how we're going to operate. Whenever they ask for an angle in the lab or I give you an angle, that's with respect to 0. So 60 degrees is like right here or so, okay? If I told you 135, that would be over here in this next quadrant. It's like 45 degrees in this quadrant, right? But the 135 we measured right there, all the way back to 0. Now, we're going to be working with trig, sine, cosine, tangent stuff. When you work with sine, cosine, tangent stuff, it's sometimes helpful to think about it as just a triangle. So when you do like tangent inverses, you're going to get like the angle inside the triangle. You're not going to get the angle with respect to 0. So we're going to have to like make sure that we don't, give the wrong answers or whatever. Because later in the lab, there's going to be like one of the last tables. You can either put in 64 degrees or you can put in 116. And 116 is the correct one because the 64 is actually just the angle inside the triangle. But we'll get there in a second. So vector decomposition, how the hell am I going to do it? Well, let's go ahead and decompose this vector that I just gave you. So I'm going to write my little coordinate grid here. 60 degrees up over here. That's 60. And then the magnitude was 50. That's the magnitude of the actual length of the vector itself. What we're going to do is we're going to look at these things as if they're right triangles, right? I can just draw a line straight down, put a little 90 on it, and then, hey, look at that. It's a right triangle. Let me go ahead and do a slightly different naming convention. I'm going to call this just F, and we're going to know that F equals 50, okay? You're going to see a certain convention that is the X component, so the horizontal component down here is called F sub X, and the vertical component is called F sub Y. This vector, this F vector at 60 degrees, it's the same thing as pushing to the right by Fx and then pushing up by Fy. So you can mimic this force F by doing Fx horizontally and Fy vertically, okay? So they're basically the same thing. Now, what I want to do is I want to say, okay, well, this force vector, I want to break it down into its horizontal and vertical components. And the reason I'm going to do that is because I want to actually add them to other horizontal and vertical components later. Okay, maybe I should go ahead and just do that all rolled into one. Might be better, yeah. So, well, yeah, let's do it all at once. How about that? So you can see it all happen at once. I'm going to call this, instead of F, I'm going to call it A. So this is A. This is A sub X, so the X component of the vector A. And this will be A sub Y, the Y component of vector A, and A's magnitude is 50. Oh, great. Okay, let me get my charger. That'll be fun if that died. Okay. So here's my A vector. I'm going to make a B vector. I'm going to make it over here. I'm going to make its length, oh, I don't know, its magnitude, its length, same kind of thing in this situation. I'm going to make it 80. And I'm going to make its angle with respect to 0, 150. Okay? So that's how the vector will be given to you. Now, what we're going to want to do is we're going to break each of these down into their components. So I've already kind of drawn out A. I'm going to do the same with B. So here's B's Y component, and here's B's X component. So let's go ahead and find these things. Now, there's a couple ways to do this. You can go ahead and use trig, which I'm going to show you right now. And you can either use well, actually, I'm just going to start with that, and then I'll tell you what I mean in a second. So what we need to remember here, some tools that we need to remember, which maybe I should like write on a different page. Tools to remember. Okay, 4 big ones. These are going to help you in this lab right now. Well, 3 big ones, I guess. We're going to have sine of some angle. Angle is the opposite side over the hypotenuse side, right? Cosine of some angle theta is the opposite side, or sorry, whoops. Okay, autopilot. The adjacent side over the hypotenuse. And tangent of theta is going to be opposite over adjacent. Okay, what do those mean? Just in case you need a refresher. If this is our angle in this triangle here, and it's a 90-degree triangle, that's important. The opposite side would be over here, directly across from the angle. Adjacent would be down here, and then the hypotenuse is the big long one. Okay, so those are the three basic trig functions. Another thing to remember is you can do a tangent inverse of your opposite over adjacent, and that'll equal your angle. Okay, so if you have opposite and adjacent, you can just flip it around, as in this inverse trig function right here, to find your angle, which is something you're going to do later on in this lab. Now, this is going to give you the angle inside the triangle, right? It's going to give you this angle. You see, it's like below B, but between B and BX, it's going to give you that angle right there. What you want to do in this lab, the numbers that I'm looking for are measured from B all the way to 0. I'm looking for the 150, not for this one in here. Okay, the tangent's going to give you the one inside the triangle when you do the tangent inverse. So then you're going to have to say, okay, 180 minus whatever this angle is, alpha or something, will give me the angle I'm looking for out here. Okay, so that's important. And then one other thing, Pythagorean theorem, which is, you know, that if you have some A, B, and C, right triangle, then A squared plus, A squared plus B squared equals C squared. God damn it. Equals C squared. Okay, so that's right there. That's another one you're going to be using. You're going to use these two to find what's called the resultant vector after you've added up your two vectors that you're given, okay? Cover that in a minute. But this is the stuff to remember for this lab right here, okay? Now going back to here, I'm gonna go ahead and apply that. So what I've been given is two vectors, right? I've just been given, there's a vector with 80 newtons at 150 degrees and 50 newtons at 60 degrees, okay? I'm gonna break each of these down now. So I'm gonna start with the A vector. I'm going to pick the sine function because sine of 60 in this triangle we have for A now, right? Because I drew that little line down so we have a right triangle. Sine of 60 is going to be the opposite side, which is AY, divided by the hypotenuse, which is A. Okay? I can go ahead and multiply both sides by A, and I get that A sine 60 is AY. Cool. A was 50, so that means that 50 sine 60 is A sub Y. Cool. Now, what you do is you just plug this into your calculator, right? Make sure you're in degree mode. We're going to be doing everything in degrees, not radians today. I don't have my graphing calculator with me. I don't know what the hell happened to it, but I'll just use my phone. Phones have it too. Hit 50, hit the sine button, hit 60, and I've got 43.3. Just a heads up, this vector at 50 newtons at 6, this A vector is the same one as they give you in the last question on the lab. So kind of already breaking it down for you. Now this next thing, I want to find the X component, right? So then what I'm gonna do is I'm gonna pick cosine this time. So cosine of 60 is gonna be A sub X over A, which is then if I multiply both sides by A, I get A cosine 60 equals A sub X. A is actually 50, so it's 50 cosine 60 equals A sub X. Okay, plug that in as well. Cosine 60 is a half, so this is going to be 25, is A sub X. All right, so I've got my A sub X, so that's the horizontal component of A, and here's the vertical component of A. All right, now, you guessed it, I'm going to do the same exact thing with B. Instead of writing out the sine and the cosine as much as I did here, I'm just going to go ahead and cut straight to it. So you can see that by looking at this line here and looking at this line here, there's kind of a pattern emerging. If I say B sine 150, I'll get B sub Y, right? And then B cosine 150 would give me B sub X. Yeah, but I'm just doing the same thing I did on the right side, but to the left side. Now, I picked 150. I didn't actually find what alpha is. Alpha is 30 degrees in this case. I didn't actually do that. Now, here's why. What's happening is to get to this point where B is pointing to, right? To get there, you can travel to the left and then travel up, right? We're talking about forces right now, but we can talk about it as if we're like traveling. You'd go to the left and then you'd go up. Okay. Going to the left on this graph is negative. All right. So if I just went ahead and said, oh, I'm going to use the 30 that's inside the triangle rather than using the 150, I'm going to get a positive answer when I look for b sub x. But b sub x has to be negative because it's pointing to the left. So a way to just avoid that issue entirely is to go ahead and just use the 150, because the calculator will know, oh, I'm in the second quadrant, I'm trying to do a cosine, therefore it's going to be negative, okay? So just use the angle they give you from 0. The only time that you want to like switch between the two is for the tangent inverse, and I'll get to that in a second. But anyway, I could have even skipped even further. I don't have to put b here, right? We know what b is. B is 80. So this is 80 sine 150. Okay, that should be 40, I think. Let's see. Yay, it's 40. 40 is b sub y. Now, does it make sense that b sub y is positive? Yes, because it's pointing up, and up in the y direction is positive. 80 cosine 150 will give me b sub x. And if I plug that in, you're going to see that I get negative 69. And I'll just round it to 69. I'm rounding today because I'm being lazy. It doesn't matter. This is just all for example. Okay. I picked a perfect number, didn't I? There. 40 for the y direction, negative 69 for the x direction. Okay. So you might be asking, what the hell do we do with this information, right? So to add vectors, A and B, break into x and y components, then add the x's and add the y's. Okay, separately. That doesn't look like the word separately, but you get the idea. X's and y's cannot add to each other. X's and x's add, y's and y's add, but x's and y's cannot add each other. Okay. Now I kind of occupied the next page here. I wish I could like tell it to go somewhere else, but okay. So continuing from here. The result of adding the vectors we will call the resultant vector. And I'll denote that with a capital R. Okay? That doesn't look like a U, looks like an A. That, you know, the result. Okay. So the result of adding two vectors we're going to call the resultant vector. Now, what we're going to do is first you want to find your new x component, right? That's going to be the x component of your resulting vector. What that's going to be is that's going to be your x component of A plus the x component of B that we found. All right? The y component of the resulting vector is going to be your A sub y plus your B sub y. Okay? Pretty straightforward so far. So we're just going to go ahead and just add those things up. Now, that negative is very important because if I didn't have that negative on here, then these x components would add, and that's not what's happening. If I pull on some object, this water bottle, if I pull to the left and I pull to the right, they're fighting each other, right? I'm not getting those forces to add. What's actually happening is they're fighting, and one of them's going to win a little bit, okay? So intuitively, we got to know they're not going to add together. They're going to subtract from each other. So that's why that negative is important there. So let's go ahead and find my resultant vector. My r sub x is going to be whatever the hell a sub x and b sub x added together is, which is 25 and negative 69. So 25 plus negative 69, and I get negative 44. Okay. R sub y, same deal, different numbers. what the hell is it? I've got 43.3 and I've got 40. Okay, 40 and 43.3. So 40 plus 43.3. So I'm going to have 83.3. Cool. So those are my new x and y components of the resulting vector, the result of adding those two vectors. And what I have now is my x and y components. I don't have the vector yet. I have the x and y components, right? So I'm not done. I'm gonna go ahead and draw it out really really quick, just to kind of show you where the hell it is. We have a positive 83 on the y-axis and a negative 44 in the. So let's go ahead and say like 44 is there, and then the scale is gonna be all goofy. Whatever. Let's just assume it's something like this. Okay, I'm not really drawing to scale too well, but you get the idea. This thing has x and y components, which I just found. That is the negative 44 and the 83.3. Okay? And I'm going to call this little angle in here alpha. I'm going to call this angle out here theta. And I want theta and r. Okay? So I want r. I don't want rx. I don't want ry. I want r. So this is where this next part comes in. These inverse tangent and the Pythagorean theorem. Okay? That's how we're going to find our Pythagorean theorem, and that's how we're going to find the angle, the inverse tangent. All right? So, now here's a slightly tricky part. I mean, just stuff to remember. I'm going to go ahead and find the angle. Now, when I do this, you're going to see that it actually isn't going to give me theta. It's not going to give me the angle I want. It's going to give me alpha. So if I say, okay, tangent of alpha is equal to this 83.3 over this negative 44, what's going to happen is, I was going to go ahead and do it for you so you see the trouble here. Tangent inverse of 83.3 over negative 44 equals alpha. If I plug that into my calculator, I hit the inverse, hit tangent, and then inside the tangent I do 83.3 divided by negative 44. I'm going to get negative 62 degrees. Now that doesn't really make any sense. It's actually telling me that it's down here somewhere. Okay? So that's not actually good. I don't want that. I don't want that negative on there. I don't actually want to I don't want to put the negatives inside this tangent thing because I know where this thing is. I don't need that negative to tell me where it is or the sign to tell me where this thing is. I know where it is, right? It's 44 to the left and then 83 up. So it's in the second quadrant. So here's what I want you to do. When you're doing the inverse tangent, ignore that negative. Okay? That's what I want you to do. Positive 44, positive 44, positive 62. Now you know that alpha is 62 degrees, right? This guy right here is 62 degrees. But I want theta, right? So to get theta, do simple little subtraction. This is 180 degrees over here, right? So to get theta, I do 180 minus the result that I got from my inverse tangent. That's going to equal my theta, right? So I'm at 180, I go 62 up, and then whatever's left over, that's the angle I'm looking for, all right? So here I'm going to find that theta is whatever the hell that is. I'm not doing basic arithmetic today. 118. Okay, I found theta. Cool, right? That's the thing that I'm actually looking for when they're saying, hey, what's the resultant vector's magnitude and the resultant vector's angle? They want that angle, the 118. They do not want the 62, okay? So, important. Now, to find r, we use Pythagorean, right? Mr. Pythag. So we're going to go ahead and do this. So we're going to say that r is the square root of 83.3 squared plus, now the negative doesn't matter here either because it's negative 44 squared is just positive, so I'm just going to just write it as that. Okay, and then now I can go ahead and compute that. 83.3 squared plus 44 squared. Using my phone, so it's much slower than if I had my actual freaking calculator. And to the power of 0.5, aka square root. And I have gotten that my capital R, my resultant vector's magnitude is 94.2. Okay, I'm just going to round it to 94 because I'm being lazy today. There we go. 94. Oh, wait. Well, 94 what? Okay. This part I can't be lazy about. It's 94 newtons. Let's go ahead and keep our units on our final answers. Okay. So there we go. That is how we are doing it. Okay. Okay. So yeah, that's pretty much all you need to know. I'm going to show you a weird special case where one of the angles or one of the vectors isn't on or is on one of the axes. Like here, I did the hardest case. Basically, you have some vector that's in the second quadrant, some vectors in the first quadrant. They both have some weird angles, so you got to break down both of them. Then you got to have the components, right? Just actually, I should just kind of summarize really quick. We had these two vectors. We used sine and cosines to break them down into their y and x components. We made sure we kept the correct signs because we know where they are. We know that bx has to be negative. Okay. We collected the ax, ay, bx, and by, and then we said, okay, well, I just need to do this now. I just need to add up the x's and add up the y's to get my rx and ry, right? So that's what I did over here. So we got this negative 44, and we got this 83 right here. Cool. I went ahead and replotted this just for my own sanity, and I suggest you do the same because it helps you remember where the hell this thing is. It's in the second quadrant. Then I used the inverse tangent, right? And I used it positive. So I just made everything positive. I used the inverse tangent to find the angle inside the triangle, this alpha right here, okay? And then because I know where it is because I drew it out, right? Now, I don't expect you to draw it out on the actual assignment because how the hell are you going to do that? Just do it on your paper or something, so your own sanity. I had to do 180 minus alpha to get the theta that I wanted. Okay, and that's what they're going to ask for in that box. They say, what's the angle of the resultant vector? It's the theta, not the alpha. All right. And then Pythagorean theorem I take the rx and ry components. Right. I just basically did r is the square root of rx squared plus ry squared, or whatever order, doesn't really matter. And that's what I did to get to 94. Okay, so you're going to do that in this weird, like, kind of confusing architecture they provided us, where they've already given you data and you're doing percent differences and stuff. So it's weird. And then you're going to do one of your own at the end. The question 2 at the very end is just basically doing this, but a little easier. And what I mean by a little easier is, one of the examples is, what happens if you have a vector that's like pointing straight up? They'll call it the C vector. They'll say it's equal to 10. Okay, pointing straight up is at 90 degrees. So they give you a vector of 10 newtons at 90 degrees. Pointing straight up. Okay, well, what the hell is this thing's x component? How far is it going to the left or to the right? Doesn't look like it's going to the left or right at all, is it? Its x and y, or its x component is 0. Okay, and then its y component, well, if the x component's 0, the y component's got the rest of the information in it. That's got to be the 10, because it is pointing all the way in the direction of 10, right? How about another vector? I'll call it D, right? Looks like an O, whatever. They give you D, and they say that it's 5 newtons at 180 degrees. Okay, what's its components? Well, let's look at its x component and its y component. Well, first of all, the y component, it's not pointing up or down at all, right? It's pointing completely flat. It doesn't have any of this or any of that. Just completely flat. So therefore, its y component must be 0, and it is. And if you wanted to verify that mathematically, all you'd have to say is, well, okay, let's do 5, what the hell, sine of 180, and that's 0. Okay, and then the x component it's got the entire force in the x direction, so the x component is the 5 newtons. All right, so in the very end, they're going to say, hey, we've got, on the second, in question 2, they say, oh, we've got 2 vectors pointing up at 25 newtons each. So you've got one like that, another one like that, and they're each 25. And then you have something at 60 degrees with 50 newtons magnitude, which, hey, that looks pretty damn familiar. AKA number A, or letter A over here. Okay, cool. There you go. And they're going to want you to find the resultant and then find the equilibrium. Oh, wait a minute. What the hell's the equilibrium? Okay. Pretty simple. Pretty simple concept there. So I'm going to tell you what that is really quick. I know it kind of seems like I'm rushing a little bit, but this lab does take a minute, so I want everybody to have plenty of time to do it. If anybody has any questions, you can message me privately inside the Zoom app, or you can say it in front of everybody. I don't think anybody's going to get any, no embarrassment here. Everybody's just as whatever as anyone else. So if there are any questions before I tell you what the equilibrium is, because I have kind of hauled ass until now. Okay. Equilibrium. So what if I want to cancel the resultant vector? Okay, what does that mean? That means, well, I mean, what if I don't, like, what if I want to figure out what vector is going to cancel the two I was given? Okay, that's really what's happening here. These two, A and B, that I was given, I'm going to have to pull on this object that's in the middle, let's just say, with some force in some direction to completely cancel out A and B. I don't know what the hell that's going to be. But what I can do is I can find the resultant vector and then figure out what do I need to do to cancel that. Because it's kind of easy to cancel one vector, but canceling two at the same time is a little weird. So that's the whole point of this, right? We're doing vector decomposition, that's finding the x and y components. We're doing vector addition by just adding the components together and then doing your Pythagorean theorem to get the actual magnitude and using your inverse trig to get the actual angle. So we found the resulting of those two vectors adding together. Now we want to ask ourselves, how do we cancel it? Well, if I'm pulling, like, if I'm, for example, this vector here, right, that when we actually found the resultant vector is like up here, and it's at 118 degrees, and it has a magnitude of 96 or whatever the fuck, 94. Okay. If I want to cancel that one, pretty easy to do. All I have to do is pull exactly in the opposite direction with 94 newtons, right? Like a tug of war. Just, if you're both pulling in the opposite directions of the same force, it's done, right? Okay. So the equilibrium vector, I can call it E. In the lab, they call it like F sub E, like what's the equilibrium force vector's like magnitude. It's got to be the same as the resultant vector. It's got to be the same magnitude, just in the opposite direction. Okay, so there's not going to be a negative magnitude. Remember that. It's not going to be negative, because you can't really have a negative magnitude in physics necessarily. I mean, well, okay, yeah. I mean, not really, right? Magnitude itself just means a value, not negative or positive. I need to pull in the opposite direction, yes, but that's taken care of in the angle. Okay, so the magnitude is going to be 94 newtons for the equilibrium vector. The angle of the equilibrium vector, though, is going to be exactly 180 degrees opposite to the resultant vector. So it's going to be 118 plus 180, which is whatever the hell that is. 298. Okay? So once you have the resultant vector, it's just really quick to find the equilibrium vector, all right? It's going to be the same magnitude every time, and it's going to be exactly 180 degrees opposite. So you just add 180 to whatever angle measure you found. Okay. Another thing is I got to mention really quick, because they do this to you in here, even though we haven't talked about Newton's second law or anything yet, and we will. They give you a gram amount, and they want you to, like, on the second table, they want you to turn that into a force amount. So I just got to tell you about Newton's second law really fast. Newton's second law is the force equals your mass times your acceleration. Okay? Force is in newtons. Mass is in kilograms. And acceleration is going to be in meters per second squared. Okay? That's what we're going to basically be doing for the rest of the lab. We're not going to do CGS units. We're not going to do any kind of, like, standard or anything like that. This is what we do. Also, for gravity, which is what we're going to be dealing with, G, in your physics classes, often they say it's 10. It is not 10. Okay? In lab, because we're actually doing real measurements and all that, we have to compare our values to real world measurements. We have to use this, we have to be as accurate as possible. It's actually going to be 9.81 meters per second squared. Okay? All right. So on one of them, there's only one that you have to calculate anyway. It tells you that something weighs 30 grams. Okay? I need to use this F equals ma to get the force. All right? But that needs to be in kilograms. So going back to what we learned in the first lab, 30 grams over 1 times, I want to cancel grams out, so I put grams on the bottom. I want to replace it with kilograms, so I put kilograms on top. Turns out there's 1,000 grams for 1 kilogram. And that really just means that every time you have a gram amount, you divide by 1,000. So 0.03 kilograms, I believe. Okay. That's what the mass is. So mass and weight we talked about weren't exactly the same thing. We'll get to that eventually, but mass is more of a measure of like how hard it is to start or stop moving something is really what it is. Okay, so well, how much stuff is there? Whatever. So I want to find the force. So the force is going to be 0.03 times 9.81. Leaving units out right now because I'm not trying to get too messy here. Times 9.81, and I get 0.294 newtons. Okay, so that's that one spot they want you to fill out there. I just kind of did it for you just because we haven't talked about this, and you probably are talking about this in your other classes, or you've talked about it in the past in high school or whatever, but just there you go. All right. Okay. One last thing that I'm gonna just remind you of something. Percent error. They ask for that, and they also ask for percent difference. Okay, here's the difference between the two. They showed you this in the first lab. They actually had these two. It called percent difference unbiased percent error, but they call it percent difference everywhere else in the lab. Somebody, every year they do this. They go in and they change things around a little bit because they think they're going to make it like nicer. And so, we're going to run into some of this where I'm like, oh, great. I haven't actually read that yet, and I didn't know they changed it. But actually, you know what? You're the second class of the week, so it might not happen as much for us. Anyway, for percent error, you do 100 times your measured minus your calculated divided by your calculated. Okay? Measured is going to be the stuff they give you, the data that they give you, because you can't be in the lab right now because COVID and all that. They're giving you data. That data they give you is measured. The one that you actually calculate using like the stuff that we did, you're going to calculate a resultant vector and its angle and all that stuff, right? That's going to be your calculated, okay? So your number goes on the right and on the bottom, right? For the rest of the lab. This next one, percent difference. And these can be negative, by the way. That's fine. This error, it can be negative. Okay. Percent difference is always positive. Oh my God. I don't even know what I just did there. Always positive. All right. So this one is 200 times the absolute value of one of your things minus the other thing. Doesn't matter which order, because it's going to make it positive by having absolute value, divided by those two things added. Okay? So it's going to ask you to do percent differences. They give you they say the resultant or the equilibrium vector is 290. Like if you were in the class, you would have measured, oh, it's 290. You're going to get something like 296 or 294 or something like that, right? Whatever. Do the math and figure out what it is. You're going to do a percent difference between those two values, the 290 they give you and then the one that you calculated, right? Or a percent error, depends on whatever the hell they ask you for. Okay. So the next thing I want to do really quickly here is just kind of walk through the lab and kind of show you what you're supposed to do, right? What the hell am I doing? There we go. Okay. So, here's the ridiculous lab. So this whole intro is them basically kind of giving you a walkthrough of what I just did. This thing right here, this fx equals f, or f equals fx x hat plus fy y hat. That's just another way to represent a vector. That's basically saying, hey, my vector is this much in the x direction and this much in the y direction. Don't worry about that. That's not something you're going to have to mess with. They're not going to ask for anything in that form, so don't worry about it. So this stuff's just intro crap, blah, blah, blah. Normally what we would have done in this lab is you would have had this little table here you can see a little picture of, and you would have had, they give you like 2 weights to hang off at 2 different angles, and then you're supposed to experimentally try to find where you could put the third weight to balance like a little doohickey that's right in the middle. It kind of like, It's got like a little X on it, and if it's like floating in the middle, not touching the sides of this container, then you know you've got it balanced, and you know. So we've done that for you, essentially, quote unquote, and that's what these blue values are. This blue value here, that blue value there. These things are just like observed quantities. Here's that 290 and the 0.6 that you're going to have to compare against. This is the equilibrium force vector that you measured in class, and then you're going to calculate one later on down over here. Okay. So what's the deal here? Well, okay, so part A, you put a couple of force hangers on there, and you try to find where the third one's going to be. What the hell is it? It's kind of weird. So, okay, so right here, table A1. See how there's a blank spot? They say 0.25, and this one's blank. Well, what you're going to do is, that's up here, it said what it was. It said it was right here. It's 30 grams, right? At 30 degrees. Oh, what the hell? Hold on a minute. I just did this yesterday. I forget how, because they just reorganized this for me and I'm messing me up. Hold on. Direction 30 degrees, magnitude, direction 210, magnitude, 2 unbalanced force vectors. Table A1. $25 grams. Okay, yeah, this is for part C or whatever. Don't worry about that. Okay, right here, this empty box corresponds to part A, and you can see they hung 25 grams at 30 degrees, okay? 25 grams, that's actually 0.025 kilograms. Multiply it by 9.81. That's the number that's going to go in this box, okay? So because you want force in newtons, all right? Now, what they did for part B, okay, hold on. I need to move pulleys around the accomplish. Set up a second force vector F2 using the pulley and hanger. Use trial and error to set F2 so the system is in equilibrium. Okay, table A1, record the magnitude and direction of the first force vector. You can see that basically what's happening here is that's 30, and then 180 degrees opposite of 30 is 210, right? So if these things are balanced, if F1 and F2 are balanced, what do you think the magnitude of this force has to be? 0.25. Okay, there you go. I'm telling you, usually I give those things away because it's just kind of like, it's confusing written and like, why the hell, whatever. Anyway, so part B, keep force vector F2 in place from part A. So the F2, that 135 degree, no, this 210 degrees at 0.25 newtons is still there. And then what you're going to do, remove the pulley and hanger positioned at 30 degrees and replace it with 2 new hangers positioned at 0 and 90. We need to make the pulleys around. Okay. So you can see here, what they did was you have this one at 30 and you have this one at 210, right? Then what they did was they took the one from the 30 away and they put it, they put in a 90 and a 0. So they basically gave it like, okay, so instead of just doing the vector at 30 degrees, we're going to put in an X and a Y component that should then be the same as pulling with whatever the 0.25 newtons at 30 degrees should be the same as pulling 0.2 at 0 degrees and pulling 0.12 at 9 degrees. Basically, they just did a vector decomposition to the 30 degree angle, 0.25 newtons thing, and they turned it into this for you. Okay. And they did all that for you. Okay. Part C, equilibrium of a system of vectors. So this is the part that actually really matters. Remove the pulleys and hangers, set up pulleys and hangers to create forces at the following angles and masses. So this is part C. This is the part that actually matters. You have, at 90 degrees, you have a 30 gram mass, and at 135 degrees, you have a 40 gram mass. You're going to convert those things into newtons, okay? Now this is the thing I'd want you draw this out, right? At 90 degrees, so straight up, put your 30 grams, which turns out to be whatever the hell, 2.294 newtons. And at 135 degrees, which is a 45 degree angle in the second quadrant, put your 40 grams, which is some other value, like 0.3 something newtons or whatever, okay? And write those down just like I did in the beginning of the lab, of the lecture notes. Like you have 2 angles, you have one in the first quadrant, one in the second quadrant. You're going to do vector decomposition on those 2, okay? So this is kind of like you're doing what I just did. Okay, so see, what you're going to do is, so this is the experimental procedure that you don't actually get to do necessarily. You put a third hanger on there and you try to balance out these first 2. And then you're going to use trial and error, and then you're going to find the angle and the mass that gets you the closest to balancing those two. They did that for you. That's right here. So in the class, in the lab, somebody was like, hey, at 290, this 0.6 newtons works pretty damn well. Okay, so that's the part that's done for you already. What you're going to do is ignore everything else now and just look at these two vectors on this piece of paper that, just like I did earlier, you're going to find the resultant, and you're going to then use the resultant to find the equilibriant, okay? What you're going to do it mathematically like I did in the lecture notes, exactly like I did. What you're going to find is you're going to get values really close to 290 in the degrees and really close to 0.6 in the newtons, okay? It should not be exactly the same. It's got to be a little different. You're probably going to get like 294 or something, and then you're going to get like 0.635 or something like that, okay? I don't know if that's exactly what it was, but just do the math and show me you did it, and we'll be good to go. Okay, so after you do that calculation, using equation, okay, this I'll talk about that one in a second. Percent difference, your calculated F1x, and, oh God, that's right. Okay, these questions here are kind of dumb. Let me get back to those. Here's where you actually do this stuff, right? You break down, look, they already gave you the magnitude. You don't even have to find you don't even have to convert it to newtons. They already did it for you. Forget about that. Okay, whatever. So you're going to find its x component and its y component for the 90-degree one, right? You're going to find the x component and the y component for the 135-degree one, okay? You're going to add the x components to get your rx right here. You're going to add your y components to get your ry right here. You're going to use the rx and ry in Pythagorean theorem to get r. Hey, sounds familiar. You're going to use inverse tangent and making sure you subtract it from 180 to get the angle of r, okay? And then, right, so that's that one, right? So you want to make sure it's the angle from 0, not the one you get from the inverse tangent, right? And then the magnitude of r must be the same as the magnitude of the one that cancels it, right? You're going to pull in the same amount of force, but in the opposite direction. So this is not going to be negative. Whatever value you get here, or whatever value you get in this box, is going to be the same value you have in this box. But this angle should be 180 degrees opposite of this angle up here, or that angle there, okay? That's the deal. Then you're going to do percent errors between the values that you just got in this box and the values that they gave you back up here in these two boxes, okay? So that's what this question is down here. Is what they want you to do, percent differences. And now question 1 and 2. Question 2 is basically just do all that again, but with different numbers. So you're going to have like 2 vectors pointing up and then 1 vector in the right quadrant. You're going to decompose them and then find the resultant, and then you're going to find the equilibriant, okay? All you really need is the magnitude, don't need the angle there. So it's just like doing it again for more practice. Okay, now one last thing, and then I'll let you guys go into your little groups and stuff. Which, by the way, hopefully I can, whatever. Okay, so this is a little strange. For the data you recorded in tables A1 and B1, what's the relationship between F1, F1x, and F1y? What's an equation that relates to 3? Well, F1 is the magnitude of that's the hypotenuse, right? And then F1x is the x component, F1y is the y component. It's like a right triangle. What's an equation that relates the 2 legs of the triangle and the hypotenuse? Pythagorean theorem, right? So that's all they want you to do is write Pythagorean theorem in here. Now, using the equation from question 1, Pythagorean theorem, calculate F1x using the data in table A1. Now, if you look at the data in table A1, it gives you F1, but doesn't give you need F1y to calculate F1x with Pythagorean theorem, right? So what I'm going to say is, pardon my French, but fuck question 1 and the Pythagorean theorem, okay? Use trig, because you can only use trig. What do you have? From table A1, you have the magnitude of the force vector F1, and you have the angle, okay? So F1 times cosine 30 is Fx. F1 times sine 30 is Fy, right? It wants you to use Pythagorean theorem, but it doesn't give you all the information for it because I don't know whoever wrote this didn't think of that. But so, I'm going to be kind of loosey-goosey on grading this part here, but if you're listening to me right now and you remember this, use the trig. Trig will just give you the answer and done, okay? It's also going to allow you to give a percent difference. So using the equation from question 1, okay, blah, 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 like I said, that's dumb. Calculate percent difference from F1y and the value. Okay, so percent difference here for F1x and then the one that you got, okay? So you use the trig to get something here, your f1x. You use trig to get, I think it's going to be like 0.21 or some 0.216 or whatever the hell it is. Do a percent difference between that and 0.2. Okay. Again, we find f1y using trig and then compare it to this value here by using a percent difference. All right. If you get a 0% difference, something's wrong. It means you didn't calculate something or you just pulled an answer for somewhere else. There shouldn't be any 0% differences. Okay. That is everything. Right here, this can be kind of confusing. I want you guys to think about this and then ask me, okay? Think about number one and then ask me. All right. Cool. So once again, we're going to put everybody into groups. I have a picture taken from the last time we did this. I think there's more people here today than there was last time, though. So we'll see what happens. But yeah, so what I'm going to do, like I did last time, is what I did last time. So I'm going to put you all into groups, and I'm going to be busy for like a couple minutes because I'm going to download all those notes that I just did onto my tablet into a file. Then I'm going to email it to myself, then download it to a file on my computer, and then I'm going to upload it to Blackboard and label it so that you can see it and work with that while you're doing this lab assignment, okay? So that's what I'm going to do first. So we get you all into groups, then I'm going to do that, and then I'll be ready for answering questions and stuff, okay? So that's what we're doing. Stop the share. Okay, now I'm going to fiddly mess around with this. A second. I had 10 rooms before. Oh, crap. Oops. That's not what I want to do. Okay. So give me a second here. I'm going to assign everybody to the rooms they were in before because I know there were some that requested and all that. Okay, yeah, so I got some more people. I don't know if you guys had, I don't think any of you guys had a specific person you wanted to work with here. Okay, Brendan, Caesar, Ethan, Carla, and Trevor don't have any requests from you guys, I don't think, so I'm just going to kind of randomly assign you. All right, when do you guys got a short end of the stick here? You're by yourselves. Yeah, whatever. Okay, you're good. There we go. Okay. All rooms are now open, so if you hit join, you should be able to, it should pop you right back into your thing. I hear somebody back there. Are you good?
Yeah, sorry, my partner just had to go.
Oh, um, okay. I can throw you in another group.
It's okay. I've kind of been working on it. We decided to just meet up on Friday again.
Oh, okay. Well, that's fine too.
Okay, thank you.